Could a battery save an entire city from going dark? Not a power plant, not a giant smokestack, not a new dam in the mountains, a battery, but not the tiny one inside your phone. I mean rows of silent metal containers sitting at the edge of the city. No smoke, no spinning blades, no roaring turbines, just steel boxes, cables, cooling systems, and software. On a normal day, nobody notices them. But on the hottest afternoon of the year, everything changes. Millions of air conditioners kick on at once. Elevators rise through glass towers. Factories keep running. Servers keep processing data. Traffic lights keep switching. Hospitals keep drawing power. And every home expects the lights to stay on. But behind every outlet, something delicate is happening. The electric grid must stay balanced every second. Too much demand, and the system starts to strain. Too little supply, and voltage can sag. One weak point can ripple across the grid. So how does a battery respond faster than a power plant? Why is it not just storing electricity? And why could the future grid need batteries the way a human body needs a heartbeat? To understand that, we need to zoom out. Because the grid is not just wires on poles. It is one massive machine, a machine that never gets to pause. Electricity begins far from your wall outlet. It starts at power plants, solar farms, wind turbines, or dams. From there, it moves through high-voltage transmission lines. Those lines stretch across deserts, plains, and cities. Then the electricity reaches substations. These substations step the voltage up or down. They act like pressure valves for the grid. After that, power enters local distribution lines. These are the lines feeding neighborhoods, offices, factories, data centers, and transit systems. Finally, it reaches your home. Your fridge, your lights, your charger, your air conditioner. But here's the strange part. Electricity is not like boxes in a warehouse. You cannot simply pile it up everywhere. Most electricity must be used almost instantly. The moment it is produced, someone must consume it. That means supply and demand must match constantly. Not once per day, not once per hour, every single second. Now imagine a city waking up. At 6 a.m., homes begin pulling electricity. Coffee machines turn on. Showers heat water. Phones charge before work. By 8 a.m., offices come alive. Lights switch on across entire downtown blocks. Elevators begin cycling floor by floor. Computers boot up. Air systems start pushing cold air through towers. By noon, the sun is high. Parking lots shimmer. Roofs absorb heat. Every building starts fighting the temperature. Then comes late afternoon. This is when the grid feels the squeeze. People come home. They turn on air conditioning. They cook dinner. They charge devices. Some plug in electric vehicles. Stores stay open. Data centers keep running. The city pulls harder and harder. To most people, nothing dramatic happens. Maybe a light flickers. Maybe the air conditioner sounds weaker. Maybe the power bill looks painful later. But inside the control room, operators see everything. They see demand climbing across digital screens. They see load curves rising minute by minute. They see which lines are stressed. They see which substations are getting crowded. They see where the next problem could appear. And they know one simple truth. A blackout is not always caused by zero electricity. Sometimes it starts with imbalance. Demand rises faster than supply can follow. A cloud slides over solar panels. Wind drops across a generation site. Transformer heats up under heavy load. A line carries more power than expected. A neighborhood suddenly pulls too much current. The grid does not fail all at once. It starts sending warning signs. Frequency shifts, voltage dips, equipment heats. Operators adjust. Power flows reroute. The whole system tries to correct itself. But correction takes speed, and this is where things get difficult. Traditional power plants can be powerful, but many cannot react instantly. Some need time to ramp up. Some need fuel, heat, steam, or spinning mass. Some are built for steady output. They are strong but not always fast. The modern grid needs both. It needs strength, and it needs reflexes. That is why those quiet battery containers matter. They are not impressive because they look huge. They are impressive because they respond fast. When the grid has extra electricity, they absorb it. When the grid suddenly needs help, they release it. In a few seconds, they can push power back. And that small timing difference can matter. It can smooth the bump before it becomes trouble. It can support voltage before lights flicker. It can stabilize frequency before alarms spread. This is the hidden contradiction. The future grid does not only need more energy, it needs energy at the exact right moment. That is a much harder problem, because a city does not consume power smoothly. It surges, it drops, it spikes, it changes with weather, habits, and time. A hot afternoon can stress it, a cold morning can stress it, a sudden demand jump can stress it. Even clean energy can add complexity. Solar power rises during the day, then it falls when the sun sets. Wind can surge, then fade. That does not make renewable energy bad. It means the grid needs a buffer, something that can catch extra power, something that can release it when needed. something that can move faster than heavy machinery. And that is the real role of grid batteries. They are not just backup power. They are not just giant phone batteries. They are shock absorbers for electricity. They catch the sudden pressure. They smooth the sharp edges. They help the grid keep its rhythm. From the outside, they look almost boring, just containers behind fences. But inside, thousands of cells are working together. Sensors track temperature. Software watches charge levels. Cooling systems protect the equipment. Power electronics shape the electricity. Commands move through the system instantly, and all of it serves one goal: keep the grid balanced. So when the city reaches peak demand, when every building pulls power at once, when the system needs help immediately, those quiet boxes can wake up. They can charge, they can discharge, they can stabilize, and they can do it before most people notice. But that raises the bigger question. If batteries can react this quickly, what is actually happening inside them? A power plant is the heart. Where does the battery sit? The answer is not where most people expect. It is not just a storage box. It is not just a backup plan. It is more like a shock absorber. It catches sudden pressure. It smooths sharp changes. It helps the entire grid keep its rhythm. Watch how the system works. When supply is higher than demand, the battery absorbs power. When demand jumps, the battery releases power. That sounds simple. But inside the container, it gets much more complex. The system is not one giant battery. It is thousands of smaller cells working together. Each cell holds a tiny piece of energy. Group those cells into modules, then stack those modules into racks, then connect those racks into container-sized banks. Now the grid has a fast-reacting energy reserve. But how does it know when to react? That is where the battery management system comes in. This is the first hidden layer. It watches the entire pack in real time. It checks temperature, it checks voltage, it checks current, it checks state of charge, it checks cell health. Also protects the system from stress. If one area gets too hot, cooling activates. If one section charges unevenly, the system corrects it. If the battery is pushed too hard, it limits output. This is not passive storage. This is active control. Now comes the next question. The battery stores energy as direct current, but the grid runs on alternating current. So, how does that stored energy enter the grid? The answer is the power conversion system. This is the next critical layer. It takes direct current from the battery, then it converts it into grid-ready alternating current. It matches voltage. It matches frequency. It synchronizes with the surrounding network. Without this layer, the battery cannot speak the grid's language. And this is where the speed becomes impressive. Traditional generators can be powerful, but they often need time to respond. A grid battery can react much faster. It can detect a shift. It can receive a command. It can release power in seconds, sometimes even faster. That speed is the real secret. The grid does not always need hours of energy. Sometimes it needs seconds of support. Just enough to stabilize the system. Just enough to prevent a small dip from growing. So what happens when frequency begins to drift? The battery sees the imbalance. The control system calculates the response. The converter pushes power into the grid. If there is too much power, it can absorb it. If there is not enough, it can release it. This is why batteries matter during sudden changes. They help bridge the gap. They give operators time. They make the grid more flexible. From the outside, nothing looks dramatic. A row of containers sits behind a fence. There are no moving blades. There is no tall chimney. There is no dramatic sound. But inside, the system is constantly watching. Sensors feed data into controllers. Controllers send commands to inverters. Inverters shape the electricity. Cooling systems protect the cells. Software decides the timing. The entire unit behaves like one coordinated machine. That is the twist. The battery is not valuable only because it stores energy. It is valuable because it controls timing. It can charge when power is abundant. It can discharge when power is scarce. It can respond when demand spikes. It can help steady voltage. It can support frequency. It can reduce stress on nearby equipment. In other words, it does not just hold electricity. It helps manage motion inside the grid. Think of a car hitting a rough road. Without shock absorbers, every bump hits the frame. The ride becomes unstable. Parts wear down faster. Control becomes harder. The grid has bumps too. Demand jumps. Clouds move. Wind changes. Equipment heats. Neighborhoods pull more power. A battery helps soften those bumps. It does not replace the whole vehicle, but it helps the vehicle stay controlled. Now let us zoom out again, because one battery site is only one layer. The future grid is not built around one single machine. It is a network of coordinated layers. Each layer has a different job. Together, they keep power moving safely. The first layer is steady generation. This can include large plants and other firm sources. These provide the backbone. They keep energy flowing across long periods. They are like the heavy foundation of the system. strong, stable, and built for endurance. The second layer is renewable generation. Solar power rises during the day. Wind can arrive in strong waves. These sources can be clean and powerful, but they also follow weather and time. That makes them different from traditional steady output. They add energy. They also add motion. The grid must be ready for that motion. The third layer is battery storage. This is the fast response layer. It catches extra power when supply is high. It releases power when demand rises. It can support the grid during short pressure points. It can also help smooth renewable changes. When solar output drops, batteries can fill the gap. When wind surges, batteries can absorb the excess. That makes the whole system easier to manage. The fourth layer is software. This is where the grid becomes intelligent. Forecasting tools estimate demand. Sensors measure real-time conditions. Control systems send instructions. Operators watch the network from control rooms. They do not just ask how much power exists. They ask where it is needed. They ask when it is needed. They ask how fast it must move. Then comes the fifth layer, the users. Homes, offices, factories, data centers, transit systems, hospitals, stores. Every user changes the grid. Every air conditioner adds load. Every elevator adds load. Every server adds load. Every charger adds load. The grid must handle all of it, not as an average, not later, right now. So what happens at sunset? Solar output falls. People come home. Lights turn on. Kitchens start running. Air conditioners keep working. Devices begin charging. The gap can open quickly. This is where the layers must coordinate. Steady generation holds the foundation. Batteries react quickly. Software gives the signal. Operators monitor the flow. The user never sees the choreography. And what if one neighborhood suddenly pulls more power? The system must decide where support comes from. Should a battery discharge? Should another source increase output? Should power flow shift through another line? Should voltage support activate nearby? Every answer depends on timing. Every second matters. The grid is not just about producing electricity. It is about directing electricity with precision. This is why the future grid looks less like a one-way road. It looks more like a living network. Power can come from many places. It can move across many paths. It can be stored, shifted, and released. Batteries become one of the fastest muscles in that body. Software becomes the nervous system. Operators become the hands on the controls. And the city becomes the demand that never stops changing. But this also raises the next question. As cities get smarter, will the grid become easier to manage or harder? Because every new device needs power. Every new system depends on uptime. Every hot day pushes demand higher. Every clean energy source adds another moving part. So the quiet battery container is not the end of the story. It is the beginning of a much bigger system. But this raises a bigger question. As cities get smarter, does the grid get stronger or more stressed? Because the modern city no longer runs on lights alone. It runs on elevators, hospitals, transit systems, cooling systems, factories, servers, chargers, and homes that never really sleep. Every new device adds another pull. Every connected system adds another expectation. Every hot afternoon pushes the network harder. And this is the strange part. The smarter the city becomes, the more flexible the grid must become. A building can adjust its temperature automatically. A car can charge overnight. A data center can shift computing loads. A home can run on solar power during the day. But all of these systems still need coordination. They all touch the same invisible machine. They all depend on electricity arriving at the exact right moment. So what keeps that machine from wobbling? What holds the system steady when demand rises fast? What happens when clean energy pours in at noon, then fades by evening? The grid cannot simply hope supply and demand line up. It needs a buffer. It needs a fast layer. It needs something that can absorb the extra power, then release it when the city starts pulling harder. That is why battery storage is moving from the background to the center. It is not just a support device anymore. It is becoming part of the architecture. Think of it like a pressure tank for the energy system. When there is too much power, it catches the overflow. When there is not enough, it pushes power back. It does not replace wires, substations, or power plants, but it helps all of them work with less stress. Now imagine the future city at peak demand. The sun is dropping. People are coming home. Air conditioners are still running. Elevators are moving through towers. Trains are pulling into stations. Servers are cooling themselves in data rooms. Chargers are filling vehicles in garages. The city is not shutting down. It is speeding up. And somewhere near the edge of town, rows of battery containers are watching the grid in real time. They do not look dramatic. They do not look powerful. But they are measuring, charging, discharging, cooling, and adjusting. They are helping the grid respond before most people notice anything changed. That is the quiet shift happening behind the outlet. Power is no longer just produced and consumed. It is stored, timed, shaped, and released. So could these silent battery sites become as important as substations, power lines, and power plants? In many ways, that is already the direction of the grid. The more electricity society uses, the more timing matters. The more clean energy enters the system, the more balancing matters. The more cities depend on constant uptime, the more fast response matters. And that brings us back to the original question. Could a battery help keep a city from going dark? Not because it is magic, not because it stores endless energy, but because it can react at the moment the grid needs help most. When the city is bright during peak demand, almost nobody thinks about those containers. They are quiet, they are plain, they sit behind fences, but inside, they may be doing the work that keeps everything steady. A battery is no longer just something inside a phone. At grid scale, it becomes a buffer, a shock absorber, a timing machine, and maybe in the future, one of the quietest hearts of the modern city.